I'm pleased to introduce our speaker for the day, Serina Diniega. Let me give a history. This was just thrust at me 10 minutes ago, so please forgive me for reading this piece of paper. Serina got her bachelor's at Caltech in math many years ago, and then she was a postdoc at the University of Arizona, where she studied models of alien dune formation. And then after that, she went to JPL for a postdoc, where she worked on mission ops and has worked in the Mars Project Office. And her research has been on the models of landform evolution, dune collisions, seasonality of Martian gullies, and erosion and restoration of polar dunes. So geomorphology of all the active things that are going on Mars today. And I think we're going to hear a lot more about those from her today. So with that, I will pass it on to Serina.
All right. So as Laurie introduced, my degree is in mathematics, and so I consider myself a mathematical planetary geomorphologist. So just to explain it a little bit, that's the title I give when I want to intimidate someone. I'm a mathematician in my training, and you'll see that coming through somewhat, not as much in this project as with some of the other projects I've done. But the questions that I ask and the tools that I tend to bring to bear on these problems that I'm exploring tend to be a bit more mathematical in focus. I like to quantify things, write things down in equations, things like that. Planetary, because I look at all the planets. I don't really care which planet I'm looking at, as long as the processes I'm considering are found on that planet and can be described through the kind of the equation and model that I'm looking at. I focus, though, mostly on Earth and Mars, and I do have a personal interest in Mars, so it's been fortunate that most of my work has been in that area in operations as well as program management up to this point. But most of the data that I work with just comes from those planets, and they're certainly a lot of fun to look at. And then geomorphologists, I look at the features found on the surfaces of these planets. Okay, so today's talk is about one of the studies I've been involved with. I'll get into exactly what these strange features are that are shown up here on this slide. These are strange linear features. We call them linear gullies on Mars. Or the subtitle, Playing with Dry Ice Blocks in the Utah Desert, which is really what most of this talk will be about. Okay. So those of you who are interested in looking into this more in depth, here's the paper that came out last summer. Additionally, when the paper came out, JPL put together a very short YouTube video. So if you want to share this with anyone else, please go over and check it out on YouTube. And then I guess this video will also be up shortly on YouTube. And then, time permitting, when we get down to the end of the talk, my studies of linear gullies as well as some other mass wasting features on Mars have led into an area that, when I have time, I'd really like to get more into, which is reviewing kind of all of the work that's been done on mass wasting features found on Mars and really evaluating, given all of the advancements we have now in resolution, in time baseline of these features for the ones that are active, which ones really are good evidence of water. So just to make sure everyone's on the same page in terms of how I approach these studies so that you really understand what perspective I'm bringing to this and the lenses through which I'm viewing these problems. As I said, I'm a geomorphologist. I focus on observables, specifically landforms, things that we can see and measure on the surface of a planet. And in planetary science, this can get really interesting because unlike the Earth, where sometimes you can go and look at something and actually go to it and study it and go back to it later if you have more questions, in this case, we often are working with a picture taken out of one place at one moment in time. Okay, and so that's the information that you have available to you. What we actually want is, of course, a full history of the place, including the beginning conditions and the changing conditions through the entire evolution of that landform that we're looking at. Okay, and this is where the interesting and really frustrating parts come in, is that you have sometimes single picture, single moment in time, and from that you've got to figure out this entire history. But it can be really cool. Landscapes record all of that information, and so it's a puzzle. You're trying to decode what that landscape is telling you about its history. And the way in which you do that is, of course, the model. And the model is what describes the physical processes that allow you to quantitatively connect the conditions, the planetary conditions, the environmental conditions, the various other input conditions, to, as you then integrate forward through time, to what you actually see on the surface nowadays. And so that's the observable. Okay. And of course, since I'm a mathematician, I tend to put these into more mathematical models. For your students out there, it's a really fun interdisciplinary area. I have to delve into a lot into physics, chemistry, all sorts of other literature to try to pull out the information I need about the conditions, as well as how do I describe these physical processes in terms of an equation. And then, of course, once you've got an equation, now you're in the math world and you can start applying various analysis tools to tease out any patterns, any length scales, any time scales that might be of interest that might help you interpret what it is that you see. Okay. So in building the physics model, there are various ways one can build this. First is, of course, analog geology. So you take something that you see on a different planet and you think it looks similar to something that you also can see on the Earth, which theoretically you know more about because it's here on the Earth and therefore it's been studied for a longer period of time, or you can even go and actually watch it, the landform evolving. So that's the basic and most common way I think these models are started. You can also, I won't go into these other two as much in this talk. The study I'm doing is starts with the analog geology and then it gets down into some other ideas. But the phenomenological understanding is when you use an intuitive idea of what processes might be involved. So I use that in, for instance, my dissertation work on sand dunes. Instead of actually thinking about the individual grains, I kind of averaged them together, applied intuition into what processes, how might I describe what happens when a dune evolves in terms of a simple equation that now I can actually do something with. And then, of course, you have first principles. So things like lava flows and such that, fluid flows and such where you can go back to first principle physics. That's another way to build up a model. Okay. And then, of course, the most important part in the scientific method is testing your model. So you've got a hypothesis about which physical processes are important. You've developed this model, and now you need to test it. And there are various ways to do this. Developing the model through different methods and seeing if you get the same result. You can take your model predictions and compare them with laboratory or field experiments, or you can compare your results with other theoretical models and see what those come out with. And then most importantly, and the reason I'm going through all this background is really getting to this key point, you have to consider the whole picture. As much information as is available. So you're considering a single landform and you want to understand how that one formed, but that landform didn't form in isolation. It's part of a planetary landscape. And so that's one way that you can really test your model is you consider all the information you have available about that surface, about its history, about that planet's history, and see if now your little model fits in correctly into that whole story. Okay. So I'm building up to this because planets can be really, really tricky buggers. And linear gullies is a case here where I really think that played a large role. And I'll get into the theories people had about how these features might have formed. So these are the linear gullies. To give you a sense of scale, they form on different sizes on Mars. The ones on the right, I can make the mouse appear. These guys are about a few hundred meters in length. And the ones on the left here, these are the most famous ones. These are in Russell Crater. This is a very large megadune on Mars. And those are about 2 kilometers long. I'm looking for a pointer. We were not finding one earlier, so it's okay. So these can form over several different scales. They're characterized by their uniform width and their extreme length. These are a few meters wide. They often have levees, which you can see in this close-up down here, which is of the bottom part of one of these guys in Russell Crater. Another important characteristic are you see at the ends here. They just kind of end, sometimes with a pit, sometimes with a chain of pits. Okay, and that's something really important to keep in mind with these features. Additionally, as they go down, we call them linear gullies because they mostly just go down the slope, but sometimes they have sinuosity. And in this example on the right there, it's got more extreme sinuosity than most of the features. Most of them go more straight down, but they can wiggle around a bit. Okay. So these features were seen in Russell Crater, especially because they're 2 kilometers long. They're a little hard to miss. But they've since been found through dune fields through the southern mid-latitudes, and I think I found a couple even more getting to the polar area. And so there's a real question about how these features may have formed. So the original theory was based on their long length, their sinuosity, and the fact that these are erosional features over low slopes. Some of these dune slopes are down to maybe 12 degrees on average. So based on that, people proposed water-carried flows, or specifically debris flows. And here I have some terrestrial examples. So this is that comparative, that analog study. And so you do see these long slopes. These things come down from the hills, starting in the steeper regions, then they extend over lower slopes. You have that convergence as you go down slope that we also see with the linear gullies. However, we have a few very different morphological characteristics, especially up at the top in the alcoves. So you're seeing that these really spread out, and they have a large drainage area. And then more importantly, if you look down at the bottoms of these, so the way that these form is you have an erosional form at the top, and then a transport area, that's the channel where material is coming from the top and being carried. And then you have a depositional apron at the bottom. Okay, and that apron is key in this case because you've physically moved material via water from the top, carried it down, and deposited it then at the bottom. So you get this characteristic triangle channel, triangle shape. Okay. Those aprons are found, that particular shape is found on other features on Mars. These are called like more classic gullies. However, you don't get these features on the linear gullies. They are characterized, one of their key characteristics is the fact that they lack an apron. They just end, if anything, they end in a terminal pit. There is no material being deposited at the bottom. Okay, and on the Earth, the only time you find a gully that has no apron at the bottom is, for instance, in this example in the bottom right corner, where you have a river carrying it off. Okay, and I can pretty much assure you there is no river carrying these aprons off on Mars, so there must be something else happening that we need to be able to explain this lack of a depositional apron. Okay, so these are the key questions. Remember, you have to go to the whole story. So the second question I listed here is, where does the debris go? Where's that apron at the bottom if these are formed by water-based flows? But then the whole question, where does the water come from? These are on top of sand dunes, coming out of the very tops, going down the slopes. So where would this water be coming from? It's not an aquifer, because it's coming out from the top of a sand dune, things like that. So those are the two questions that people have really studied this debris flow model. They've looked at the sinuosity and tried to tie the morphology of these things and their sizes to exactly how much water would be needed. But you need to go back and answer these questions. Where does the water come from? And then where is the apron if these are water-driven flows? Okay, and so here I've shown an example. So on the right, of course, is just the Martian example. On the left here, people have done a lot of laboratory experiments trying to figure out then how you could do this with water. And this is one of the better examples. This is Vetty et al. 2008. And in this case, these are about centimeter-sized flows. I think they're like 1 or 2 centimeters across. And this is one of the few examples I found where they were able to actually get a kind of similar looking morphology. In this case, they had a very carefully controlled trickle of water coming out of the top of the dune. And it created the levees, and it did not create the aprons. It kind of had a little toe at the bottom there, but there's a few problems with this one. These are only centimeter sized. Trying to scale this up. This is a very carefully controlled trickle of water, and then they also have an impermeable layer underneath it. So it doesn't answer the question of where does the water come from. And then if you try to scale this up to a few meter wide, it's really hard to imagine how that might work, how you're going to get enough water to make a couple meter wide feature, but still be trickling out very slowly. And then, of course, you have all the problems of how water behaves on Mars. And so this is the closest that the water flow people have come, I think, to explaining these features. And so I propose, myself and a group of scientists, we propose a different and we think far simpler and way more fun theory. Okay, so what about a dry theory? So the originator of this idea is Candy Hansen over at PSI. She works on seasonal processes on Mars, so she spends a lot of time staring at these images and looking at how dry ice behaves on Mars as it accumulates during the winter. As probably all of you know, the Martian atmosphere is mostly made up of carbon dioxide, so that's really the volatile that we're working with on large scales in the winter time. So every winter it accumulates across these surfaces through the mid-latitudes, and then in the spring it sublimates away. And so here's a picture of Russell Crater, that dune with the linear gullies, and you see these black spots are where you're getting a bit of preferential sublimation in those areas, and then you see the linear gullies coming down over the slopes. Okay, so we know that this happens every winter. So she wondered what would happen if one of those blocks fell onto the sand, and okay, that sand's a bit warmer, so maybe this is more of a block falling down a slope thing than water carrying material. Okay, so she worked out this theory. When warmed, you have a dry ice block that'll sublimate, so it's going directly from solid to gas. This will create a cushion of gas under the block. So maybe this block could then, even over low slopes, kind of slide down and maybe kind of carve out these channels that we're seeing. Okay, so that could maybe work. And then the block gets down to the bottom of the slope and it stops, but even though it stopped moving, it's still going to continue heating up and sublimating. And so it continues kicking out all this sand and digs out a pit. And then as it continues warming up, eventually the block disappears, so you end up with a pit. So you would end up with a track and a pit once you get around to summertime. Okay, so qualitatively, this seems like this theory might work. And so we go to high-rise observations and we see, do we see anything that might support this idea? So in the top left, if I get my mouse working, we have little pits that have formed on a dune slope. This is actually on a classic gully apron on a dune. So it's one of those alcove channel apron ones down in the depositional apron. So we know when that sand was laid down, you're getting these pits that form. And they weren't there before the winter happened, and then they're there in the spring. So we know that they formed over that season. And some of these, if I can get the mouse to work, there we go. So you have a pit, and some of these have channels that extend from them. And most of them you can kind of trace out. These are very small channels. They're about 1 meter wide. You're right at the limit of high-rise resolution. But we know that these formed over the winter season. So okay, this could kind of work. Here on the upper right are two images that are separated in time. And this is not a dune. This is in fact a sandy crater wall slope. And you can see that there are these new features that have formed these channels with pits at the bottom. Okay. And then additionally, in the bottom images, you have these white dots. This is within Russell Crater, within those linear gullies. Over the winter, we've started noticing these white dots that appear. These are 1 to 2 meters in size, and they disappear in the summer. They're bright dots appearing at the end of winter, disappearing in the summer. Pretty sure, and you're not going to get 1 to 2 meter sized water ice blocks. So it has to be carbon dioxide ice blocks. All right, so we've got all the pieces. We've got channels and pits that are forming in the present day during the winter. And we have large 1 to 2 meter sized dry ice blocks that are within these features. So now we just need to test if this mechanism can actually work, because we haven't actually seen it happen yet. We've just seen all the pieces. Okay, so I ended up going out to Utah for personal reasons, and that's where Candy is located. And so I said, hey, you want to go meet up and do some science? And she said, sure. So we bought some dry ice. Okay. And we went out to a dune. Okay, so on this first video, these are not dry ice blocks. That is Candy up at the top there. And she is pushing a water ice block. And she is attempting to put it down the steep side of a dune slope. And as you can see, the water ice block won't budge. It gets wet, the sand sticks to the bottom.
I'm not going to bother recording that time.
It gets sand stuck in front of it. It doesn't move. Water ice would sublimate on Mars, yes.
It rolled a little bit further.
And then we have a wooden block, we figured it wasn't going to do any better, but just to see. Wooden block about the same size, and again, you can see Candy strenuously trying to push it down that slope, and it won't move. So then we pulled out the dry ice blocks, okay, and we expected something more exciting to happen than that, but we were pleasantly surprised. Same dune slope. Just play that again. Like I said, fun theory. Dry ice isn't that expensive. Make sure you've got some gloves and a dry dune. Take it out, it's loads of fun. So we discovered that dry ice on the Earth, admittedly, under a hot Utah sun, will behave significantly different than water ice blocks or wooden blocks on a sand dune. And it's that sublimation activity just is enough to lift it off that sand and completely lubricate it. No problem at all going down that slope.
What was the slope?
So that was the lee side, so assume about angle of repose on average. So it's pretty steep, 33 degrees. Oh, thank you. Yes, he had asked about what the slope of the slope angle was that block had slid down. Okay. Now, when you have a dune, so this is my dune scientist side coming out, you have the downwind side, which is about angle of repose, and the upwind side of these Barken dunes, this is coral pink sand dunes up in Utah, is at a much shallower slope. So we wanted to test out, can these blocks maybe do anything exciting on the shallower slope? Because like I said, on Mars, on average, some of these slopes we're looking at are more around 12 degrees, and that's been a big piece of evidence that people have used for water, is that things don't roll down 12-degree slopes, especially if they're sand and they can get stuck. So this is about a 6-degree slope. And every time it kicks up a cloud of sand, that's it going through a footprint or a ripple. It did not stop for anything except eventually the bushes at the bottom. We managed to terrorize a few lizards that day.
It's still going.
Like I said, loads of fun. Take some dry ice, just make sure you got gloves on.
Wow.
So, all right. So we determined the answer to this first question is clearly yes, this process can work. Dry ice blocks will in fact move over low slopes for long distances. So now the question is, will this create the right shape? Okay, and here I have some pictures. Yeah. We did do, the question was if we looked at different size blocks. As I'll get to toward the end of the presentation, blocks come in pretty much one size. Apparently, there is a standard mold that everyone uses for making dry ice blocks, which is 10 inches by 10 inches by 10 inches. So the biggest you can get to is 10 inches by 10 inches, and then however thick they'll cut it for you. We did have smaller ones, which we also buried in and made pits and such. But yes, all of the blocks, anything from 5 inches by 5 inches to 10 inches by 10 inches, they all behaved about the same way. Mm-hmm. Oh, that's an interesting idea. So then you're getting more mass on top, but you're not changing the amount of sublimation, because what's sublimating and what matters is the surface area that's in contact with the hot sand. So we did not try that, but I mean that would just be a thicker block. Yeah. All right, so just as these pictures show, we do get it, but I'll show the videos. I'll get to you, Ramsey. So here you can see this block sliding down. This is in Kelso Dunes. We went out with a bunch of JPLers and raced dry ice blocks down the slope. The reason I wanted to go out to Kelso is it's a gigantic dune, and I wondered how far these things would go. And at least one block, I'm pretty sure, made it all the way to the bottom. So it went about 600 meters. But as you can see in that video, this block, despite the fact that it is hovercrafting, it is in fact carving out a shallow track. So measurements we made in Utah, this is, you know, 1/8 of an inch. It's not a very big track, but it is leaving a track. And then some of the experiments that we did, we repeatedly sent a block down the same track to see if it would deepen it. And it did very, very slowly. Okay. And here's just a close-up of a block that had come down and stopped at my foot. This one was especially vigorously sublimating. You can see the sand appears to be boiling around it, carving out these round areas. That's how hard that gust was pushing out against that sand. So, Ramses, did you have a question?
I still see it bubbling.
Mm-hmm. Definitely. I'll get to that in a later slide. He'd asked about how Mars conditions would change the dynamics. The sand temperature in Utah was about 98 degrees Fahrenheit. It was very warm, not Mars conditions. So that definitely plays a role. Kelso Dunes, the air temperature, I didn't measure the sand temperature, but the air temperature was about 72, so it was quite a bit cooler. And the blocks went slower, but they still moved. That was not a problem. The only thing that will stop these blocks, as long as you're above the temperature of dry ice, is if it's wet, because then it'll freeze to the water. You need that surface layer to be completely dry. So. Oh, and just in this picture, just wanted to highlight, in this bottom right picture, this is a block that we had just left on the surface for about 10 minutes. And you can see all the little channels that the gas was carving out underneath. Candy was excited. She studies spiders on Mars, if you're familiar with those. Those are features that form underneath the slab ice. And you have the bottom of the slab sublimates because the sunlight penetrates through and heats the bottom of it, because that's where the darker sand is. And it'll carve these channels and then eventually explode out in little jets where they converge. And so she was really excited about seeing spiders actually forming in front of her. But yeah, this sublimation was obviously very, very vigorous in Utah, but it would be happening, like I said, on any surface that's warmer than the dry ice. Okay. And then the last question is, can you get the sinuosity? So remember that this is again a key piece of evidence that people point to when they say this looks fluvial. There must be a fluvial mechanism behind it. And so here are just some examples, though, and this is one of the things that finally got this whole study moving forward in terms of we have to do an experiment, is we saw these pictures of boulders that had rolled down. And so those left two pictures, A and B, are Martian boulders that have gone down a slope, and you can see that as the boulder is itself irregular, or it might encounter some topography, it mostly goes down straight downhill, but it wiggles around a little bit. C there is a terrestrial pebble that has rolled down a dune surface. And then D this is a slightly different mechanism, but these are snowballs that have formed and rolled down the slope. So it's a little different there because you're accumulating material as you go down the slope. But again, you get this nice sinuosity that's happening. So it seemed that sinuosity itself should not be a barrier for looking at a dry theory that involves a block moving downslope versus a fluvial one. And so we did not look at rolling blocks because, as I said, our slabs were, they were definitely slabs, not blocks in our experiments. But even with the slabs where they're more sliding as opposed to rolling, so this is the track that you're seeing that was laid down. This is a block that had been put down about 10 times down the slope. And you can see that what happens, it creates these small levees on the side. And they're very, very small, but they are enough that it starts interacting with its own levees. And so if perhaps on Mars, winter after winter, you had a block forming, falling down into a pre-existing track from the previous winter, you would have this sort of repeat activity. And these things start start wiggling around on their own. She just put it down every time and let it go, and it slowly widened its track, and then it also started wiggling around. So
the levee walls are starting to...
So I'd say success there as well. All right, so we've answered, yes, this mechanism works. Yes, you can get the right sort of geomorphological feature, and yes, you can get this sinuosity. Okay, now the question, will this still work on Mars? Okay, it works in a very hot Utah desert. Mars, you're coming out of winter, you're not going to have as large a temperature difference between the sand and the dry ice blocks. Even if that sand is exposed sand, it still just isn't going to be 98 degrees Fahrenheit versus the dry ice temperature. Additionally, the gravity is different, the air density is different, and so one of my colleagues, Jim McElwain, he's a mathematician, and so he had worked on a model to calculate the max time that a block could be levitated due to sublimation. So he just looked at if you have a slab, and in this case you don't have to worry, the height ends up not mattering as much because you're considering something that extends out. So you just have this surface area where the gas is forming and creating a levitation force. And so you're looking at the heat difference and how that translates to how much gas is coming out, and is that force enough to actually lift its own weight? Okay? And so that's how he calculated the force that would be generated, and then this max time, as this block is going, it's not only gaining heat from the sand, but it's cooling the sand down beneath it. So what's that max time that the block could continue to be levitated if the sand is coming to equilibrium with the block? And then you compare that with the time that a block would need to move such that it's over new sand. So it basically moves its own size forward, and now it's over newer, theoretically hot, fresh sand, just due to gravity and neglecting friction, because this is nearly a frictionless environment. Okay. So on the Earth, using the temperature conditions that we had, and Earth's gravity and all of that, we got a maximum time on the Earth's scale of 5 seconds for the blocks that we were using. Like I said, about 10 inches by 10 inches were the largest ones. And the amount of time that the block needs to move to the new sand before it would have dropped is significantly less than that, less than a second. 0.27 seconds on an angle of repose slope and half a second on the 6-degree slope. So as we saw with the experiment, on the Earth, these blocks should have no trouble whatsoever moving. They are going to just be moving down that slope fast enough under their own weight that they're constantly encountering new, hot, fresh sand, so they're going to continue to be levitating and continue moving forward. Okay. So then we took those equations and applied Martian conditions. Those are the results. It ends up, the difference in gravity and the difference in air density and the way in which the sublimation process happens end up kind of canceling each other out for blocks of about the same size. So we again got 5 to 6 seconds for the levitation time. And then the time needed in order to move forward due to the lower gravity is a little bit longer. It was about half a second at the angle of repose slope and a full second for the shallower slope. But again, you have far more time that you're levitating than that you need to move. So it should be no problem. And then if we scale up our blocks to the 1 to 2 meter size blocks that we're actually seeing in the high-rise images, now you need more time in order to move that distance forward, but it still is less than the levitation time that our model is predicting. So we predict, based on this, that the dynamics that we saw here on the Earth would in fact translate pretty well over to Mars. And so what we were seeing should be happening on Mars every winter. So this is a first order model. We have an MFRP now to develop it further, so there's all sorts of second order effects we'd like to add in. For instance, once you actually lift the block, you've changed the thermal coupling between the block itself and the sand, and so that's going to change that heat flux, which changes the sublimation rate. But Jim is working on all of those aspects and trying to understand better. But to the first order, we think our model is still, it holds water, let's say, unlike the other one. So, summary of results, yes, resounding yes. Dry ice blocks will definitely move down shallow, even shallow dune slopes, as long as they're dry. And yes, dry ice blocks can carve out the tracks that appear similar to what we see on Mars and create pits. I didn't show pictures, but we did bury some blocks. We also left them sitting on the surface and then measured the sizes of the pits that were left after the blocks had completely sublimated away. And in this case, we were using smaller blocks because we didn't want to be out there for days. You know, the size that would disappear in a few hours. And very shallow pits. We're not quite creating yet the scale of the features we're seeing on Mars, but I think we're getting there. So the main open question is that scale difference. We're looking at smaller features, smaller blocks, so perhaps the much larger features on Mars, though, are due to the repeat seasonal activity, and then also much larger dry ice blocks. I think it was Ramsey say something about a human-sized dry ice block. That would be awesome. If anyone knows where I can acquire one, I would love to do so, although then I'll have to hire a team of undergrads to get it to the top of a dune, because these are fairly heavy blocks. I have been informed by several dry ice suppliers that I could not possibly want a block bigger than 10 inches by 10 inches by 10 inches. This is just ridiculous. It's already 50 pounds. And I'm like, you're not understanding. I'm a scientist. This is my experiment. And they're like, no, you do not need a block bigger than that. So I've checked. Caltech apparently buys theirs from the local grocery store. So I haven't yet found a place. We're some point when I have time and money to do so, we're thinking of like some sort of wire cage to string a bunch of blocks together. But yeah, it would be fun to do this again with a much larger block. Okay. So the next steps we're continuing monitoring of the changes on Mars. One thing that we've really discovered, and this is where I've been active in several areas of looking at present day activity on Mars, is because I work with high-res images. And these high-resolution images, we've now got enough of a baseline that we're really starting to pin down timing of present day activity. And that timing has turned out to be a very key piece of information. There's a lot of stuff that once you understand the timing, you realize that various theories, you can start to knock off various theories and support other ones. So today is the end of southern winter in Mars year 32, and we're continuing our monitoring through the winter season of gully activity and linear gully activity, and this will extend through September. We are going to do more laboratory experiments. Jim McElwain is the PI of an MFRP, you NASA people out there, grant to do laboratory experiments under controlled Earth and Mars conditions, and so that we can really get to more of the details involved with what these dry ice blocks are doing when they're on that surface and they're levitating and they're moving. And then, yeah, field experiments with larger blocks of dry ice would be pretty awesome. So I'll pause here. Do we have any questions about this? Otherwise, I'll get to discussion. Yes?
The two blocks have flat surfaces.
Yes.
On Mars, there might be irregular surfaces with peaks and valleys. How would that impede the flow?
So the full question was about the shape of these blocks. In this case, we were looking at slabs. I think that if you had an irregular block, that's definitely going to change how it sublimates, because now the surface area actually in contact with the sand is significantly less. But you will have more rolling action. So I think you're going to be looking at a slightly different movement, but I don't think that's going to prevent these blocks from moving down these slopes. Does that make sense? Yeah.
I have a question. Why is tau larger?
Hold on a second. If we're going to do questions now, we might as well use the mic.
Okay.
Can we use the mic?
Sorry, Laurie.
Okay.
Why is tau larger for the larger blocks? If the surface area is the same and you don't have friction and you're going down the slope under the force of gravity, why does tau change?
I think we did have the length scale. It has to move forward a further distance to get to fresh sand.
Oh, so the surface area is bigger, not
Yeah,
just not just the.
Yeah, we're not.
But if it were just a weight issue, tau should remain the same.
Exactly. In this case, tau is related to how much time does it take the block to move.
So the bigger
fresh
block
sand.
had a bigger surface area.
Bigger length, further distance to get to fresh sand.
Okay,
Yep.
so it's a linear function of that.
Yep.
Okay, okay.
Yeah.
I thought a bigger block was just a thicker block.
Right.
No,
Jim McElwain's a good mathematician, and he quickly got rid of the height aspect.
Okay.
Since Laurie's there.
Yeah, two questions. How are the blocks formed? And corollary, why are there just this number of blocks? Why not less? Why not more?
Good question. So in terms of how the blocks form, the modeling of that still needs to be done. We know that CO2 accumulates on the surface, and theoretically it can compress itself under just gravity, the crystals sintered together, and form more like slabs. This is known to happen in the polar regions, and then this is now thought to be also happening maybe in the mid-latitudes where we're seeing these features. And then we do see blocks, so we know that somehow you get from frost that's accumulating on the ground to these blocks that appear to have moved and are coherent and disappear as a unit, as a block kind of sublimating from all sides as opposed to a loose pile. So that's thought to be happening. The other area that is an open area of research is how many blocks and what size should they be forming. So I know some people who are looking now at that problem of modeling that formation of the CO2, and then it would, as it sublimates, the entire, you're getting weakening in certain spots, and so it should break off. And so they're looking at the strength of that CO2 and seeing at what size perhaps one would expect blocks to be breaking off, and how often, how many, is there a particular time period where this should be happening? But yeah, all good questions. Yeah.
So the obvious follow-up experiment is to fly a piece of dry ice to Mars and push it off a dune. But until you're able to do that, I was wondering if what the reaction was of the water people, and if you've converted any of them to dry ice people.
We've been trying. People are now starting to do more experiments using dry ice in the laboratories and such, but there are still an awful lot of abstracts where they hook up a hose to the top of a slope and watch the water go down. And for some of these features, water may still play a role. In fact, if we get to the discussion, I'll touch on that a bit more. I kind of upset the water people sometimes. but I think people are coming around more to this idea, and that's where that timing, knowing when this activity happens, has really been important, because we see this activity happening and it's in winter. It's at the very end of winter, beginning spring, when the surface is still covered by carbon dioxide. So you know that generally the temperature is much colder than you would get liquid water at. And that's not even addressing the question of where does the water come from. So, yeah.
Well, I've got a water-related question as well. For both substances, you're in a portion of the phase diagrams where no liquid phase exists, so they both sublime. Mm-hmm. So how do you know that water ice wouldn't do the same thing on Mars?
So Jim McElwain did look at this, and I'm trying to recall the details of it, but it has to do with the rate of sublimation. Water will sublime on Mars, but the way in which it does not provide enough lift force. It has to do with the lead-in frost effect and all of that. Thank you. Yes, it has to do with the way in which it's sublimating given the atmospheric composition and all of that. Thank you. Yes. And so he did model that and determine that water would not do it even if you had somehow a block that size. Yeah.
Okay, let's do one more question and then let Serena finish. I saw one more hand over here.
Just a simple question, like great talk, Serena. So as far as like CO2 condensing, are these features preferentially located in certain areas, and is that consistent with rates of CO2 condensation in those areas?
Good question. All right, I will use that to segue to the rest of my talk. So this is an area that I would like to be able to spend more time on in terms of doing science. I recently presented a poster at the 8th Mars conference, and in fact, I'll put a shout out to that. It's loaded on the 8th Mars site if anyone's interested as an e-poster. So here, I've been trying to compile that information about these different features, and some key information that one has to look at is where are these features found. Linear gullies, in particular, are found on sandy, slopes. They could be dune slopes, or they can be just sandy crater wall slopes. They're always pole facing. This is one thing I really noticed. They're different from other features. You can get a dune crest line that's running roughly north-south, but they meander around a little bit. And you have a pole facing, so you have linear gullies form. There are none. There are linear gullies. There are none. They're very clearly, I've never found a linear gully not on a pole facing slope. So that definitely strongly implies some sort of relationship with volatiles and seasonal frost. And then these are all in mid-latitudes where you can see CO2 frost accumulating across the surface. So all of those definitely imply some sort of relationship with volatiles. And then their activity is in the spring. So this is a very abbreviated version of my full poster where I've been trying to isolate what are the key pieces of information that one should look at in order to ultimately get down to the question I have at the bottom: do these features possibly involve water? Can we treat them as evidence of water? And so here are the linear gullies. In this case, all of the evidence here points to something involving seasonal processes and most likely the CO2 frost. And then the dry ice blocks seem to be the simplest explanation for what we're seeing. The other area that I work in are these classic gullies, the alcove channel apron gullies. And again here, I won't go into it in the talk, but we see activity at the end of winter. So we are proposing for these as well a seasonal frost-related formation process, at least in the present day. And there's still a question of whether or not in a past epoch these were related to water formation. One of my colleagues, Colin Dundas, had just put out a paper where he was looking at the modification rates of these features on the crater walls, and he thinks we can explain all of them with seasonal processes. And if there were any that had previously been formed via a different process, those should have all been degraded and modified such that we can't really recognize them anymore within the time scale for when seasonal processes would have formed all of the observable features. So yeah, the water community, in terms of linear gullies, I think people have really come around. The classic gullies, we're still facing some resistance, but people are starting to come around. We've been working on this for a few years now. Okay, and then just I filled in a few more pieces at the bottom, some different types of slope, various mass wasting features, slope features that people at one point or another have pointed to, except for the boulder tracks. Nobody's pointed at that one for water, I think. But everything else people have pointed to at one point or another due to the size, the length, the sinuosity of these features pointed to perhaps a fluvial mechanism. And the only one that really so far seems to imply a fluvial mechanism is the RSL. And the key piece of information here is that they only are active in the seasons with the warmest temperatures. They are different from all the other ones in that case. And so that's Alfred McEwen and his group are really looking at these RSL. If you don't know about them, I recommend looking them up. They are the best evidence, in my opinion, of present day, perhaps water on the surface of Mars. Okay. So, like I said, if you're interested, you can go to the 8th Mars website and view my e-poster, which has a lot more information. Like I said, the goal with this is now we have all this new information. People have made all these interpretations based on subsets of the available information at various points about these slope features, and I'd like to re-look at it and really identify what information is it that one can use to say, yes, this is more likely based on water flow, since that's, of course, a driving question in the Mars community. I would also like to put out there that just because most of these features maybe are not related to water, that doesn't mean that they are not really interesting features. These linear gullies are formed by dry ice blocks that fall, giant dry ice blocks that one would never find here on the Earth because we don't have dry ice blocks except for in freezers at grocery stores, certainly not 1 to 2 meters in size, falling onto a slope and then hovercrafting down these slopes. I want to be the astronaut standing at the bottom of that hill. That would be amazing. Or even better, snowboarding down it. So thank you very much.
Cool. Okay, I'm going to ask 2 questions. The first is, while you were in Utah or at the Kelso Dunes, did you fold up a blanket and put it on top of the ice and sit on it and try to slide down the dune?
They were too small.
But did you try?
We had we had plastic trays, and we did. But
did it work?
we had plastic trays that we put on top, but it didn't help any.
You need to work on that.
We have this vision of maybe getting a cat and strapping it to the top of a block, because then that would be YouTube gold right there. But we still, I think, need a larger block to support the weight of the cat, and we would have to very much protect the cat from the dry ice effects itself.
Okay, hold on, I have one more question. And I asked this of pretty much anybody who studies this sort of topic. You noticed that there were changes from one season to another in some places, so that's how you constrained it to early spring. Have you noticed any interannual changes? Are there some places that are more active than others? Have some places become centers of activity that weren't previously, and so on?
We have not, I think, tracked that down for linear gullies. In the other gullies, we have seen interannual changes, as you know, with Candy Hansen. She's been really looking at those features on the dunes, the Alcove Channel apron. The linear gullies, it really just blossomed last year. Any students looking for an internship? A fun project. These high-rise images are available online. It just takes some good looking through to really identify the changes that are happening and quantifying it. So, good question.
Okay. All right. You pointed to this guy here.
I have a question about density. With water ice, I mean, there's solid blocks and there's snow of various densities. And have you done any experiments to try to figure out when how dense the dry ice would be on Mars under the Martian conditions? Well, you can't simulate the gravity, but you can simulate other things.
Right. So in our modeling, I think we use kind of an intermediate density. So one that would be a coherent slab, but a fully coherent slab of dry ice would be, I think it's 1,600 kilograms. It's more dense than water. So we chose a value less than that. In terms of what's known about dry ice on Mars, people have tried to estimate that from looking at how much, the column density of CO2 on a surface, and then looking at its approximating the height of it. But I don't think we don't have specific measurements for specific areas.
Would low density dry ice facilitate or inhibit the sliding?
Well, you have less weight pulling it down. But that's true. You also have less volatile. I would be concerned about
surface area.
I think it depends too if it's kind of uniform density, like loose grains versus pockets. Because if you have pockets, then you're going to really change how it's sublimating when you hit those pockets. So I think it would depend at that point on really what the internal structure is looking at for exactly how that's going to change how the sublimation goes. Yeah, I'm not sure.
But the ice that you bought dry ice you bought commercially here on Earth, that was all pretty much maximum density stuff.
Yeah, they were pretty heavy. They're not greatest quality. You could find cracks and pockets in them. But macro scale porosity. I think at the micro scale, they were much more uniform and very dense. Yeah.
Okay.
There's obviously a lot of dust on Mars. Have you looked at what would happen if dust was deposited in with the carbon dioxide? Would that make it more or less likely to sublimate and form a lead and phosphate layer?
I don't know. I also don't know how that would change the formation of the blocks to begin with. That's a good question. I do know one thing we noticed when we were out in the field is you had the block of water ice and sand blew across it, and the whole thing was just this muddy brown by the end because, of course, all the sand stuck. But the dry ice sublimates, and so you'd pick it up and shake it off, and all the sand would fall off, and you had this pristine block again, which I thought was kind of interesting for this difference between the two. So.
Could you show the very first title slide? Yes. Besides the linear features, notice that underneath there are also linear features going in different directions. I presume those are probably the tracks of dust devils?
Yeah, those darker Streaks, yes. Yeah.
Yeah, so there's a connection with dust.
Mm-hmm. Yeah.
Well, great. That was a great discussion, everybody. Thank you. Let's thank
you
Serina.
all.
And Serina, we'd like to present to you this SETI mug that we give to all of our speakers, so you can put dry ice in it and see if it floats down a dune. Thank you very much. Great. Thanks for coming. And I apologize for the warmth.
Bring it to dry ice, I'll take care of it.
Yeah, totally. Yeah.